So, very good evening to all the participants. Now we have the speaker named Dr. Daasari Surender. Now I would like to introduce the speaker. Dr. Surender began his academic career as an assistant professor at Kamala Institute of Technology and Science, affiliated with JNTU Hyderabad, where he served from 2020 2012 to 2017. He then pursued a full-time PhD program at National Institute of Technology, Silchar, under the guidance of Professor Fazal Ahmed Talukdar and Dr. Taimur Khan, completing his doctorate in 2022. Currently, Dr. Surender is an associate professor at Bhagyeshwari College of Engineering. In addition to his teaching responsibilities, he has contributed significantly to the institute's administrative and academic functions, serving as IQAC members, IT coordinator, project coordinator, member secretary for the academic cell, and research and development cell in charge. He is a valued member of IEEE and a fellow of IET. Dr. Surender has published approximately 30 international journals, conference papers, and book chapters. His research interests are centered around planar antennas, dielectric resonator antennas, and energy harvesting systems, reflecting his dedication to advancing the field of electronics and communication engineering. So, thank you, Dr. Surender, to be here and for giving a valuable time. So now I will request you to start your presentation.
Thank you, sir. Thank you for your nice introduction. Okay, I'm going to start, sir.
Okay, you can start.
Okay, sir. My talk is on designing an efficient antenna and rectangular systems for RF energy harvesting applications. As already discussed by all the authors, so the utilization of the rectangular systems and RF energy harvesting applications nowadays. So present days, the utilization of the batteries are increasing every day, day to day, because consumption is increasing, and also we are depending on the battery vehicles nowadays because of the scarcity of the and increasing rates of the fuel, and so due to that, we are highly depending on the conventional batteries. So this increases the sometimes so it is increases the scarcity also. So now we need to depending on the alternative approaches of the alternative approaches for the conventional batteries. So alternative approaches or mainly energy harvesting approaches are mostly suitable for replacement of the conventional batteries. So before going to that, first I would like to introduce about my college. My college is Bhagyeshwari College of Engineering Autonomous, and it is accredited with NAC A++. And the courses offered in our college are diploma, UG, and PG programs are offered. So total 3,150 students are now enrolled in the different programs in our college, and various UG and PG programs are also MBA, MCA, and in MTech, CSE, ECE, EEE are available, and BTech, CSE, AIML, CSD, ECE, EEE, Civil Mechanical are available in our college. So this is the outline of my talk. So first of all, before going into the talk, first I would like to know that what is energy. First, energy is the qualitative property that must be transferred to an object. So generally, this word is derived from the ancient Greek, and there are two types of energies: kinetic energy and potential energy. As we know that energy generally, kinetic energy is derived from the energy of a moving object, and the potential energy is generally absorbed from the static object. And various energy forms from the potential and kinetic energies are light, RF, thermal, and mechanical sound. So first, and before that, what is energy harvesting and its need? So before going into our talk, first of all, we would like to know that what is energy harvesting and its essence, its need. So energy harvesting is a process of means gathering energy from the ambient environment. So energies may be different. solar, wind, acoustic, thermal, different types of energies are available in the nature. So collecting that energy from the from the ambient environment and using that energy for low power electronic devices, and that process is generally called energy harvesting approach. So, and the necessity of the energy harvesting is its utilization. We are utilizing properly the ambient energy which is efficiently available. That is the most important thing. And second one is we are actually nowadays we are depending on the conventional batteries. By energy harvesting approaches, we are lessening the dependent on conventional batteries. Due to that, and one more thing, here the conventional batteries lifetime is less, so we need to replace every time. So that increases the complexity as well as the cost. Sometimes, in case of implantable devices, these electronic devices also sometimes instruments sometimes we also use in medical applications. So in medical applications for proper like patient condition. So to know the organs conditions, whether they are perfect or any uh, proper condition will be giving by these instruments. So if we use the conventional batteries for those, if we attach conventional batteries for those devices, because of the lifetime low life lifetime, so we need to replace those devices frequently. That increases the complexity and it increases the cost also. But by using energy harvesting approaches, the cost will be reduced. The cost will be reduced. And also, we are utilizing the ambient environment, so it reduces the environmental pollution also. And that extends the lifetime of the battery. So various energy harvesting sources, various energy sources available in the ambient environment are geothermal, wind, solar, hydroelectric, nuclear, biomass, etc. And this is the comparison of different energy harvesting approaches. So I have here mentioned only 4 energy sources, harvesting from 4 energy sources. So here we can see clearly that the RF energy harvesting is continuously available compared to all other energy harvesting approaches. And nowadays it is increasing every day. And because of the continuously available, the conversion efficiency of the RF energy harvesting approach is comparatively more than the other energy harvesting approaches. And here the device is lightweight and compact compared to the solar energy harvesting, thermal, piezoelectric, and all other energy harvesting approaches. And the thing is here the only drawback is the power density is less compared to all other compared to some of the energy harvesting approaches. The density is less. However, it is available continuously. That is the better thing in the RF energy harvesting approach. So various reasons that are attracts the RF energy harvesting approach. Their installation is easy and its compactness and the availability is increasing day to day and continuously available, and it can be available, it can be operated in indoor as well as the outdoor environment efficiently. The other the problem with the other energy harvesting is it is not possible to operate some of the energy harvesting devices are not operated in the indoor environment. But by using RF energy harvesting approach, this drawback can be eliminated and power conversion efficiency is more. So various RF and power sources are intentional, means dedicated. So anticipated, unknown means so unexpectedly some energies will come, and unknown sources. The intensity of various energy levels of the various power sources are mentioned here clearly. And first of all, what is RF energy harvesting? RF energy harvesting is the most commonly used harvesting approach. Here in this, we utilize the ambient RF energy and convert that RF energy into the DC, direct current, that can be utilized for energizing low power electronic devices. And here it is the process of capturing electromagnetic energy from the atmosphere and convert that into electrical direct current. Here in this RF energy harvesting approach, basically a device that name is rectenna rectifying antenna is used. Basically, the rectenna comprises of antenna, RF input filter, impedance matching network, rectifying circuit, and storage element, the energy storage element. Here, the antenna is the front end element of the rectenna system, and that is most important device, because in rectenna, as the power received by the antenna is more, then get we can uh, we can expect more power from the output. If the antenna receives less power, then it is not possible to increase the power from the output. So the selection of the antenna is important for designing the rectenna system. And here, first rectenna invention. The rectenna was invented in 1964 and was patented in 1969 by US electrical engineer William C. Brown. And he was demonstrated the rectenna with a model helicopter, which was powered by microwaves transmitted from the ground, received by the attached rectenna. So the related images were shown in figure 2. And the introduction about the rectenna system. Rectenna is a special device for the RF energy harvesting applications. And here it comprises antenna, filter, impedance matching network, rectifying circuit, and load storage element. Here the antenna is already discussed. It is used to collect the ambient electromagnetic energy. And based on the frequency, there are various types of energy antennas are found in the rectenna system, or single band antenna, multi-band antenna, broadband antenna. Based on the operating frequency of the antenna, here the rectennas are also classified as single band rectenna, dual band rectenna, multi-band rectenna, broadband rectenna. And here the desired characteristics of the antenna are operating frequency is the main important characteristic for the antenna in designing the rectenna system. And high gain is also important characteristic parameter to increase the receiving power. And here the directional properties also plays an important role in designing the antenna for the rectenna system. Here to increase the applications of the rectenna system, the size of the rectenna plays a major role suitable for applications, different applications. Here the rectenna size is less. If the rectenna size is less, then we can extend the applications of the rectenna for several devices. So the band of frequencies that are suitable for RF energy harvesting approach. So here the main thing is in RF energy harvesting approach, we are utilizing the ambient energy, that is freely available energy from the ambient surrounding atmosphere. So when we design the antenna for the rectenna system, we must select the appropriate frequencies that are available surrounding us. So the various band of frequencies that are available in the ambient environment are AM that are given in the table. So here nowadays the applications of 5G are increasing. In mid-range 5G applications are millimeter wave frequencies, and also increasing the Wi-Fi frequencies, Wi-Fi 6E. Those applications are also increasing nowadays. So the availability of the frequency energy levels at those frequencies are increasing day to day. My suggestion is the researchers, those who are designing the antennas, better to choose the frequencies that are available plentifully for the design of the rectenna system. Otherwise, it is not possible to apply for the practical applications, because in practically without having energy levels, it is not possible to test that but designed antenna in the ambient environment. So my suggestion is design the antenna where the available energies nearby you. And DC pass filter, there are various filters are low pass filters, generally band pass filters. And here in this, basically band pass filters are used for band pass filters are used, and because it allows the certain band of frequencies and to remove the harmonics that are created from the fundamental frequency of the antenna. So to remove the harmonics, so generally we use the filters after the antenna. And the matching network, as we know that the matching network is play an important role, because the matching network basically that matches the impedances of the antenna as well as the rectifying circuit. If the impedance is perfectly matched, then maximum power of the received power by the antenna is transferred to the rectifying circuit. Then it is possible to get it can be expected more power from the rectifier output. And the rectifier circuit. Rectifier generally converts the received energy from the matching network to the electrical DC. So here diode plays an important role, and selection of the diode is also important for designing the rectifying circuit. So basically for RF rectifier circuit, we basically use a Schottky diode for conversion of the received signal by the matching network. The most frequently used Schottky diode families are HSMS 28XX, means in that 2860, 28660, 2820, basically the 2850. This type of generally we use for the rectifying circuit, and MA4E1317 and SMS 7630, etc. Mostly used rectifying circuits are single series diode, single shunt diode, full wave bridge rectifier, voltage doubler rectifier, and Greenwich rectifier circuit. And here the impedance of the rectifier is a function of input power as well as the frequency of operation and load resistance. And here the so the power conversion efficiency of the rectifier can be increased by choosing an appropriate diode and by choosing an suitable rectifier configuration. Rectifier with wide dynamic power range is very important to stabilize the performance of the rectifier. Then we can get more output from the rectangular system. And some characteristic parameters of the Schottky diode. Various Schottky diodes are presented in table 1. You can see clearly that here, and HSMS 2850, 60, 2820 are from Avago manufacturer. And here we can see that for the SMS 7630, the threshold voltage is very less. Its value is 0.09 volts, and breakdown voltage is also less. And comparatively, all other Schottky diodes, here the HSMS 286B has, and MA4E1317 has more threshold voltage. And when we see the breakdown voltages are also almost equal. And for the breakdown voltage for the HSMS 2820 is large over the presented Schottky diode model. Here, in choosing the diode for the rectifier design, we must consider the available energy levels. As the available energy levels are more, in that case, the available energy, if it is more, then we must choose the diode having large breakdown voltage. Otherwise, that diode function may be stopped because of the high power levels, high energy levels in the ambient environment. So when high energy levels are high, we must choose the diode having large breakdown voltage. And when the power levels are less, we must choose the diode having less threshold voltage. Because even the power levels are low, the rectifier function should be started. So in order to start the functioning of the rectifier, we must choose the diode having low threshold voltage for the rectifier design in rectangular system. Here the performance characteristics of a rectangle is characterized by the receiving ability of the antenna and the power conversion efficiency of the rectifier circuit. Here the antenna harvesting power increases with a high gain characteristics and a multi or broadband characteristics. The power conversion efficiency of the diode is generally calculated using this power conversion efficiency equals to DC power by input power to the rectifying circuit. And the rectangular efficiency is usually calculated using this formula, DC power by power captured by the antenna. That is the efficiency of the entire system. And here the performance enhancement characteristics of a rectenna. The rectenna performance mainly depends on receiving ability of the antenna and power conversion efficiency of the rectifier circuit. So first we will go to antenna performance enhancement methods. So to get more power, basically antenna is the front end device. So we must focus on the antenna to get more, to collect more energy from the ambient environment. As I always think that if the power received by the antenna is more, then we can expect by choosing the appropriate rectifying circuit, we can expect more power from the rectenna system. So because of that, I always prefer to design an efficient antenna for the rectenna system. The harvesting power by the antenna can be increased by a high gain antenna or multi or broadband characteristics of the antenna, circular polarization characteristics. And here the circular polarization also plays a major role, because if the polarization mismatch is there, then we cannot receive maximum of the transmitted energy from the by the rectenna system, by the antenna. Because if the polarization is different, then the receiving antenna, usually antenna in the rectenna system is used at the receiving site. So the antenna at the antenna designed in the rectenna system cannot collect maximum power available nearby that antenna. So due to that, polarization is important. So if the polarization mismatch is there, then maximum power cannot be harvested by the rectenna system. So the polarization is also important, because a circularly polarized antenna can only receive any polarized signal from the ambient environment. So due to the reason, antenna is mainly due to that reason. So circular antenna with circular polarization is important for designing the antenna for rectenna systems. And the desired properties of the antenna are omnidirectional characteristics, directional characteristics. When we are highlighting RF energy harvesting system, the omnidirectional characteristics are important, because the omnidirectional antenna can receive energy from any direction around that antenna. So that is because in RF energy harvesting, the transmitted antenna is unknown to the receiver. So in that case, the receiving antenna with omnidirectional can helps to receive energy from any direction. So that is the important thing. And directional characteristics are helpful when transmitter is known to the receiving side. So then only directional characteristics are essential for the receiving antenna, when we know the transmitter direction. And a suitable frequency chosen, that is also is already discussed. Suitable frequency is important for the antenna design, because of energy levels, based on the energy levels. And compact in dimension is also discussed. The compactness increases the applications of the rectenna system. So various miniaturization approaches. So here in this we have I have presented a few antenna designs which are based on the compactness. Here circular approaches geometry is implemented in the presented paper for achieving the compactness. And here in this we can see that here the dimension of the antenna is around 30 by 30. It is very less. So it is almost equivalent to a size of a coin, 1 rupee coin. So it produced, and it has also given a good conversion efficiency. And in this system, here in this it is used voltage doubler rectifier circuit. And here from this we can see that the low antenna gain is observed with compact antenna dimension. And here the voltage doubler rectifier is used for converting the signals. And here the power conversion efficiency and output voltage are good at optimal values of the load. And here in this, Coates fractal geometry has been implemented for getting the compactness. And here the efficiency of the efficiency, and it is the coach fractal geometry with rectifier incorporated. Embedded rectifier is implemented. Integrated rectangular system is implemented. Integrated rectangle is presented, and here it is shown that the power conversion efficiency of the rectangular system is given maximum of around 66% is observed at 5 dBm input power, and the maximum output voltage observed is it's almost 9 volts at 10 dBm input power levels. And the fractal geometry is also presented. And in the fractal geometry, in fractal geometry is also presented, and here it is observed that the output voltage is maximum output voltage observed is around 2 volts at 3 dBm input power level. And here Mindel line approach and Sierpinski fractal geometry are also presented. And these are the different approaches are used for achieving the compactness. And also Hilbert fractal geometry and tapered slot geometry. And here, but the thing is, as the size of the antenna decreases, the gain of the antenna is most of the cases, not every time. So most of the cases we observe that. So as the size of the antenna mainly affects on the gain of the antenna. So this is the challenging task in designing the antenna for the rectangular system. The compact antenna, designing a compact antenna with high gain is highly essential for rectangular applications. So one more design, that is dual U shape of slats. U-shape of slots and edge cutting helps in obtaining the resonance at the desired operating frequency here in this. And here aperture slot is circular aperture slot is introduced in the here in this aperture feeding approach has been used. Here in this, a circular aperture slot is incorporated in the incorporated for electromagnetic interaction in between two substrates. Here, when we see the radiational characteristics of the antenna, here this shows that clearly the E and H planes are presented, giving omnidirectional characteristics. And this antenna is mainly designed on Rogers substrate, and the thickness of the each substrate is around 0.8 mm, and the dimensions also given. It's around 30 by 30 mm square. And here we can see that the matching is good at 3.5 gigahertz frequency, and gain obtained at the maximum gain obtained is around 5 dBi at the operating in the operating range. So this is also these here dual U shape of slots also helps in increasing the gain. So the various techniques adopted by different authors for getting the antenna miniaturization, and the comparison is also presented. And here it is clearly noticed that the reduction in antenna dimension affects on antenna gain performance. And here Sierpinski fractal geometry provides a better gain performance of the antenna with a small dimension. And fractal based geometry is the most adopted technique to achieve compactness. And now we are focusing on gain approaches. So here some of the articles that are presented to give the better understanding that in figure 13 here it is shown that a traveling DR LA, that is dual rhambic loop antenna. Here in this only one pair of dual rhambic loop antennas are presented in figure 13, and here in figure 14 array of DR LA antenna here use characteristic that need to be polarized antennas are presented in figure 16, A, B, C, and D, E, F. Here 16, and here the maximum gain observed is around 5. And when we use the array of antennas, the gain is increased to around 15 dB. So that is the advantage of using array of antennas. With the array of antennas, the gain can be increased. And here, and RF to DC conversion is also. We can see clearly that an array of antenna elements enhances the gain of the antenna, and the effect of the array of elements onto the circularly polarized is minimum. We can see output. Overall, collects more amount of energy from the ambient environment that can supply to the succeeding elements of the rectangular system. Therefore, we can expect maximum power from the rectangular system. And this is also one of the mechanism to increase the gain of the system. Here in figure 18A, this is the single feeding, and in B, the differentially feeding antenna. So here in table, it can be seen that the single-ended antenna, that is single feed antenna, gives the maximum gain of 3.55 dBi, and the differential fed antenna gives 5.47 dBi. It's almost 2 dBi increment is observed in using differentially feed with differentially feeding approach. And the power conversion is also observed. Output power and the efficiency of the antenna is also given in D, 18D. It can be seen that here the power conversion efficiency of the rectangle 1 and rectangle 2. Here the rectangle 1 compared to rectangle 2 power conversion efficiency more, that shown with the red color. And the output of the rectangle 2, that is rectangle 2 is designed with a differentially feed antenna. In that gain is more, and the output is expected is also more. That is, it's almost at 150 or to 250 dB microwatt per centimeter square. It is almost 7 microwatts of power is observed by using the differentially feeding approach. Here we can conclude that the resonant frequency of the antenna is much affected by the differential feeding approach. Resonant frequencies are almost same. Even we use single feeding antenna, differentially feeding antenna. And also dimensions of the antenna is also independent of the number of ports. And multi-port device nowadays, its applications are more. So we can apply for many devices using multi-port device. And the differential feeding approach enhances the rectangular gain output. And this is also one of the article in that it is shown that dual port device. It is a dually circularly polarized rectangular system, and in this aperture coupled feeding approach has been used. Here we can see that port 1 and port 2, and it is easily observed that different ports, the output power observed at different ports in figure 19E. It can be seen that at power density of 0.5 milliwatt per centimeter square, we can observe clearly that around 3 volts of power has been received by the design rectangular system. And the efficiency is also almost equal at both ports 1 and 2. And here in this, so one of the antenna, that is hexagonal shaped patch antenna. Here in this, so here this antenna provides the gain of around 6 dBi. Here we can see that incorporating the notch. Here in this, we can see the difference of without a notch and with notch at the ground plane of the antenna. Here, by incorporating the notch, here the impedance matching performance has been increased, And we can also observe the performance in gain. That is, increment in gain is observed by incorporating the notch at the resonant frequency. At the resonant frequency, not at all the frequencies. So at the resonant frequency, we can observe the increment in gain performance. And the next one is the pentagonal shape. Here, slot loaded approach has been used at the ground. So here, the slot loaded approach is implemented to control the operating frequency of the antenna. And here, the gain operating frequency of the antenna, here in this, the maximum gain observed is around 6 dBi. And these are two different antenna structures. In figure 24, it has shown that antenna with a reflector. Reflector is also one of the technique to improve the gain of the antenna. But the thing is, by using the reflecting plane, the size of the antenna gets increased. So that increases the rectangular system size. So, and one more approach is using the multi-stack. That is multi-layer structure approach is also one of the technique to improve the gain of the antenna. So here we can see that clearly in figure 25, B and C figure, B figure and C figures, we can see clearly that here in C, as the number of layers are 7, with no air gap, the gain is around 5, and it is decreasing with increasing frequency. When the air gap is incorporated, the gain is increased. And one more thing, when the number of layers are less, then gain of the antenna is also expected less. And here, this is single fed and differentially fed antenna arrays also presented by one of the authors. So here also it is similar type of observation has been made that here differentially feeding approach provided more gain comparatively the single fed antenna array. So that is clearly given in the table, and the approaches were given in the figure 26A and B. And the efficiency is also given in the 26C. And one more approach is perfect electric conductors placed adjacent to the sites, at the sites of the substrate. So that is also one of the technique to improve the gain of the system. But by using this technique, the antenna size increased, overall antenna size increased. That increases the rectangular system gain, rectangular system dimension also. And here, by incorporating the perfect electric conducting, the performance variation can be observed clearly in figure 27B. It can be seen that when no wall is present, we can see the performance with black color line, and when our perfect electric conductors are incorporated, then we can see the performance in gain that is presented in figure 27B. And one more thing is array of T-shaped elements which are given in 28, and that is also giving a better results. That is the using of array antenna elements also increases the antenna performance, gain performance. That is also presented in figure 28C. And few of the techniques, they are suspended square plate antenna, and one more thing is slotted rectangle. And antenna gain enhancement approaches, which are observed are high gain of the antenna can be possible by large aperture and using array of antennas, and can be increased by using multi-layer structure and by placing a reflecting plane at the bottom of the antenna, and can be increased also by using dual feeding approach, and also increases by using superstate approaches for increasing the gain of the system. So these are the performance. This table shows the performance comparison of different antennas using different approaches. Here, this is the model. Here, differential feed antenna array provided more gain compared to the other energy harvesting approaches, other mechanisms of the antenna. And various circular polarization approaches. One is unbalanced slots and two peripheral cuts and diagonal directions, symmetrical strips along the diagonal direction and U-shaped slots. And these are the elements are used, these are the approaches were used for getting the circular polarization characteristics. And this is one of the best article that was published in IEEE antenna IEEE letters. So here the beauty is here the antenna was the authors were used a cylindrical dielectric resonator antenna, and a sectoring approach has been used by the authors for reducing the size of the antenna, and also they twist the antenna to increase the gain. And here for getting the circular polarization characteristics, and a metallic strip has been incorporated onto the surface of the twisted rectangular twisted circular dielectric resonator antenna. So here it is, the dimensions of the antenna are very less, that is 35 by 35 mm square, and the substrate dimension was, it is around 1.524 mm. Here the substrate for the dielectric resonator is acoustic HIK K10 material has been used by the authors for designing the dielectric resonator antenna. Here, this is the performance at various design levels of the antenna R. So at antenna 1, we can see clearly in table 2 that the antenna 1 is operating, that is antenna with cylindrical dielectric resonator antenna. So that is observed at 6.66 frequency and 7.34. When sectoring has been implemented on antenna 1, the operating frequency has not been changed much, but improvement in gain performance has been observed, that from 6.53 to 7.55 maximum. And when twisting has been done, then a drastic change in operating frequency as well as the impedance matching levels were observed in antenna 3. And when a metallic strip is attached to the incorporated onto the surface of the dielectric resonator antenna, twisted dielectric resonator antenna, there is no change in the operating frequency, but a small variation in gain performance has been observed, as well as the impedance matching performance also observed. Here the better thing is, by incorporating the metallic strip onto the surface of the twisted dielectric resonator antenna, a better improvement in AR performance has been observed. Here the radiational characteristics also presented. And here in figure 35, it shows that here the authors were presented electric field distribution at different angles. So it can be seen that at pi equals to 0 degrees, so it is observed that the electric field lines are upward, and when it is observed at 90 degrees and shifted to left, so it can be seen that these electric field lines are rotating in anti-clockwise direction. So by observing that figure 35, we can see that electric field lines are rotating anti-clockwise direction, then it is right and circularly polarized antenna. So this is the rectifier circuit configuration for the antenna, for the rectanna system for the same paper, and the complete rectanna is presented in figure 39. And here the performance of the rectanna is also observed without and with matching network. Rectifier performance that can be seen clearly in figure 37. See, here without matching network, the performance is very poor. When it is incorporated matching network, the performance is increased drastically. So that can be observed clearly in figure 37C. And a good matching in performance characteristics were observed in figure 38C. And various multi and broadband approaches. So this is one of the approach to observe dual band characteristics. So here, a slatted approach has been used with the dumbbell shape of slot in the ground plane. So here the rectangular dielectric resonator antenna is used, and by incorporating different slots, triangular shape of slots onto the in the ground plane, here the resonance characteristics observed at 3.45 and 5.79 gigahertz. This antenna is designed for dual band characteristics at for 5G as well as Wi-Fi applications. And the maximum gain observed by the antenna is 6.441 decibels. And the experiment for the experimental validation and the radiation characteristics were presented. And another broadband antenna geometries were presented. Here, coplanar waveguide structure, gradual flaring structure, slotted ground, fractal geometry, and slotted approach. Different, and one more thing is rectangular and annular slots. Slotted approaches are highly adopted for getting broadband characteristics. It can be observed. And a comparison of various techniques to design broadband antennas are presented in the table. Here it is, a coplanar waveguide feeding approach is suitable to provide broadband characteristics. And here, effect of a multi-band configuration on rectangular performance. The significance of designing the antenna with multi-band characteristics are presented in figure 45. Here we can see clearly that so the RF to DC power conversion efficiency and DC output power in figure 45, it is observed here that here when number of sources are 2, 1, that is with blue color line, that is with light blue color line, that is when one RF source is used at 0.9 gigahertz, the power conversion efficiency is less. When number of sources are increasing, we can observe that the increment in RF DC power conversion efficiency. So, and similarly, the similar kind of performance is also observed with the increasing number of RF sources. That can be shown clearly in figure 45B. Here, DC output power is increasing with number of RF sources. Here we can conclude that in this from this one, the increase in number of input power levels to the rectangular system increase the power conversion efficiency as well as the DC power. So this is really a wonderful article. And a multi-band antenna configuration. Some of the geometries that were presented for achieving multi-band characteristics. And here various approaches to achieve DLR multi-band characteristics were given in the diagram. That a slotted loaded approach provided better results in obtaining multi-band characteristics. And this is one of the article. So here, to improve the gain of the system, the defective ground structure has been employed by the authors to achieve the better performance. And here, this defective ground structure not only increases the gain, but also increases the number of also increases the operating level, operating frequencies. Initially, without the defective ground structure, the antenna is operating at 2 frequencies, but by incorporating defective ground structures, here we can observe that here the antenna operating frequencies are increased as well as the gain also. And here, this is the proposed design. Here in this, this is suitable for broadband. This is implemented for broadband case. Here, this antenna efficiently operated within 5.44 to 8.36 gigahertz operating frequency. Here in the first case, here sectoring approach was used for compactness, for overall size of the for reducing the overall size of the antenna. And one more thing. Overall size of the antenna. Here different approaches. Here step-by-step mechanism to implement the proposed antenna is presented. In the slide itself. Here the sectoring semi-cylindrical dielectric resonator antenna has been chosen for the antenna design. A bow tie slot surrounded by two sets of semi-annular slots on the ground plane has loaded in the structure to enhance the antenna impedance bandwidth and gain and axial ratio performances. And this is the best paper in my profile. That is this is spiral facet approach. This is implemented with spiral facet approach. Here in this, the beauty is the spiral facet, the number of spiral facets increases the number of resonances in this. So first we have chosen a rectangular dielectric resonator antenna with coaxial probe feeding. So here in this, we can see that gain performance of the optimized DRE antenna. Here in this, we do not use any spiral facet onto the any face of the dielectric resonator antenna. So this is the basic design 0. So that is operating at 5.8 gigahertz with a gain of around 7 dBA. And these are we have implemented in this paper. We have implemented 4 antennas by incorporating different spiral structures, optimized spiral structures on different faces of the dielectric resonator antenna. Here, design 1 is the, here in this we have used a spiral facet structure on left face, that is negative Y axis of the dielectric resonator antenna. And design 2, spiral facets were attached on negative Y axis and positive X axis. And in design 3, spiral facets were pasted on negative Y, positive X, and negative Z faces. So different structures were implemented in this article. Here, this is the step-by-step mechanism of the spiral structure. And here we can also observe the performance at various design levels. Here, this is the proposed spiral facet structure and its equivalent circuit. For the mathematical analysis, we have used this approach to calculate the resonant frequency of the antenna. And we have taken this for mathematical calculations in the article. So, and these are the field distribution patterns for the design 1. Here we can see that for at different angles, phase angles, we can observe the electric field pattern. So here it is observed that at 0 degrees it is, and by we can observe the difference in electric field orientations. So here the electric field orientation, as the phi changes, electric field orientation changes in anti-clockwise direction. So from that we can see say that that antenna is providing right and circularly polarized signal. And these are the various electric field distribution patterns of the different antennas. And the performance characteristics of the antennas of different antennas are presented in figure 62. Here we can see that, and performance comparison is also presented for the different antenna designs. In table 6, in figure 63, we can see that it is design 0, that is basic reference design, which is the rectangular dielectric resonator antenna without any spiral facet onto the surface. That operated 5.8 gigahertz frequency. And the antenna 1, that is given in figure 63b, antenna 1 is operating at the same frequency, but it is offering circularly polarization characteristics by incorporating a spiral facet structure on one face of the electric resonator antenna. In figure C, we can see that here, by incorporating 2 spiral facet structures on 2 different faces, here the 2 resonances were observed that were presented in table 7. Here operating frequencies were observed at 5.03 and 5.8, and here the circular polarization characteristics are observed at 5.8 gigahertz frequency itself. And by in figure 63D, here by incorporating spiral facet structure, 3 spiral facet structure, we observe 3 resonances. And in D, in figure E, and 4 resonances were observed by incorporating 4 spiral structures on different faces of the dielectric resonator antenna. Here the important thing is the number of resonances were controlled by the spiral facet structures pasted on the different faces of the dielectric resonator antenna. And those spiral structures were optimized spiral structures. Oh, these are the antennas. And the performance comparison. And this is the rectifier circuit, and the mathematical formulation for the rectifier were presented in the manuscript. So here in this, we have used voltage doubler rectifier for designing the voltage doubler rectifier for designing the rectifier approach has been used, and the staircase approach is used for the matching network for getting the proper impedance match. And here in this, these are the different rectangular systems implemented with different antenna designs. And the next one is impedance matching network. Impedance matching network affects. It is also play an important role in rectangular performance. So here the matching network is used to transport maximum of the received power by the antenna to the rectifying circuit. So basically, if the matching is perfect, as we know that from the impedance matching maximum power transfer theorem, as that is maximum power can be transferred to the load when load impedance is equivalent to the complex conjugate of the source impedance. So in case of that is almost it is the impedances must be, in case if we consider the real impedances, in that case real values, the impedances should be equal indirectly. So if the impedances are equal, then maximum power can be transferred to the rectifying circuit. So that performance, the effect of the impedance matching network onto the rectifier performance was clearly mentioned in figure 70, that here without matching network and with matching network is clearly presented. And it is easy to, and one more thing, the impedance matching is easy to achieve with single band operating frequency. And when in case of multi-band frequencies, the complexity of the complexity is increased in getting the proper impedance matching between antenna and rectifying circuits. Usually, L section matching network is found to be suitable at a single band operating frequency. And these are the different matching network designs for multi or broadband cases. So here, in case of a multi-band RF, multiple RF branches. So in that case, and in figure 71, it is given that in case of multi-band or broadband cases, we have taken, it is better to take different branches. So in that, each and every branch need to be matched with certain frequencies that are available in the antenna. So stacking approach is important for your stacking is important for achieving the proper impedance matching when multiple bands are available. So this is the structure summary on different impedance matching topologies. So for single band, L section is highly utilized for achieving the proper impedance matching. And for multi-section or stack of impedance matching network is used for achieving the proper impedance matching in case of quad band and 6-band antenna configuration. So here we can give some summary on impedance matching topologies, that a multi-band matching network is suitable at multi-band frequencies than multiple single-band impedance matching networks. And a star and these are the frequency source operating over broad range of frequencies, and these are the various challenges in designing the Rectana system. And applications of Rectana could find in wireless power transmission and implantable devices. And it is unknown source and dedicated is intentionally designed antenna. So these are the different mechanisms of measurements setups. One is measurement in anechoic chamber, and in figure 42 it is showing that measurement usually done in ambient environment. So wireless power transmission. So basically wireless power transmission consists of two approaches, near field and far field. In near field inductive transmission, two resonant coils were placed near to each other. So in the near field capacitive transmission, alignment usually for far field transmission we use antennas. So here in this, the antenna with directional radiation characteristics are preferred for wireless power transmission application in the case of far field approach. And a high gain antenna to enhance the transmission efficiency. And a circularly polarized antenna avoids the polarization misalignment issues in the rectangular system for wireless power transmission. Wireless sensor networks. So these are some of the designs that were used for wireless sensor networks. And medical implants. Nowadays, applications of Rectana energy harvesting, RF energy harvesting, or energy harvesting approaches are increasing for medical implants. So in medical implants, usually for accessing the information of the patient minute to minute. So in that case, the conventional batteries doesn't help much. That doesn't provide the information frequently. Sometimes even if they fail, in conventional battery fails, then the patient information cannot be known. So in that case, sometimes the situation may be worse. So energy harvesting approaches are highly suitable in case of medical implants. And also reduces the patient, like that extend the lifetime of the battery. So it is not needed to replace the batteries every time. So that is not that is highly convenient to the patient. So these are some designs for medical implants, and their performances are also presented in the table. So here in this, two different coils operating at two different frequencies were presented for medical implants. Usually, in case of medical implants, two devices, like one is placed outside the, like inside of the body, and the other one is placed out of the body. So here the transmission is usually done in the case of near field. So here, not to, like in near field, it is the device which is placed inside in medical implants, it is needed frequently the battery. So to avoid the frequent interruption, so one device is placed out of the body that supplies energy continuously. Energy continuously, then patient health condition can be accessed frequently. And this is the summary on near field harvesting. So in near field approach, a small coefficient of coupling is observed and quality factor is low, and misalignment issues were observed, and it is highly resonant, but it is limited to short distance. And these are some devices for medical, for wearable devices. And in solar power transmission, Rectana is also used here in this. And some of the performance enhancement approaches of the Rectana. So here the output of the performance of the rectenna is increased by increasing the input power level, one of the thing, and by increasing the number of rectifier stages. Usually we think that as the number of devices increases, the power conversion, dissipation power also increases, then how the power is increased. So here it operate here. This is not the actual criteria. So by increasing the number of rectifier stages, the power performance is increased. It is clearly observed. Here the effect of number of stages onto the rectenna output voltage is presented clearly in figure 78C and D. In case of one stage, the performance is very less. As the number of stages increased, then the performance also increased. So this is the summary on multi-stage rectifier circuit. It is also here we can see that when we are designing the rectifier for low power design, so in that case we must design the rectifier with minimum number of elements. So that is given. It is also observed that a rectenna in a low power design performs well with the minimum number of elements. However, a high power design performance is good for the maximum number of antenna elements. A further enhancement in rectenna performance is observed with multi-band input for a multi-stage rectifier circuit. So here it is also observed that in addition to the power required to be more, component losses also increase as the number of voltage multiplier stages increases. So this is the one of the approach to improve the rectenna output. Here, this is the RF combining circuit and DC combining circuit. So here we can see that RF power combining approach is suitable when RF energy is to be harvested. Here in this, we can see that energy to be harvested by individual antenna is low. Here, the thing is, RF combining approach is suitable when RF energy is low in the ambient environment, and DC combining circuit is used when ambient RF energy is high comparatively. So these are the two different approaches. And first we combine the RF power level, RF signals, and the combined signal is converted into the DC. So that is generally observed in RF combining circuit. And DC combining circuit, we convert the energy individually by using the separate rectifying circuits. After that, we combine the DC generated by individual circuits. That is usually observed in DC combining circuit. DC combining circuit is appropriate when RF energy levels are high in ambient environment, and RF combining circuit is appropriate when RF energy levels are low in ambient environment. So this is given. Thank you. Thank you for your support. If any queries, you can ask me freely.
Sir, am I audible?
Yes, sir. Yes, sir.
So, sir, thank you very much for your nice and valuable presentation.
Sir.
So now I will ask all the participants to raise any questions if you have.
Hello, sir.
Yeah.
Please.
Actually, I have one question. Thank you, sir, for your nice presentation.
Thank you.
As you have written in the slide that L-type section,
Yes,
matching
it is
network
single
is
band.
suitable for single band. So
Yes.
I have a question for broadband. What type of matching network is required?
So for broadband, usually it's so in case of broadband, actually designing the impedance matching network for multi-band and broadband somehow difficult
Okay.
But in case of broadband case, so there are different approaches. One approach is like dividing that entire frequency into some ranges. Then we distribute into like a stacking approach. That is also one approach.
Okay, sir.
So LC section is better for designing the broadband rectifier.
Okay, sir. And one more question, sir. As you have designed many antennas, and
Yes.
its substrate is Roger.
Yes,
So,
Roger.
sir, what will be the price of Roger? As I have,
Roses, actually it is available in my department, so I never purchased. So it
Okay.
is available around below 1,000 only.
okay, okay, sir.
Yes.
Thank you, sir.
Okay.
So, dear participants, do you have any other questions? Any other questions from any participant? Okay, I think that there is no further questions. So, thank you once again, Dr. Surender, for your valuable session.
Thank you, sir.
Now we are ending this session over here. Now I will ask participants for their feedback.